research with some colleagues here. As maybe you have already known that we have Aljabar research group in Indonesia, and we are part of this organization.
Good.
Yeah, it's still a little bit of very active communities. I think many activities, algebra in mathematics in common, and this is our activity. We have regular Kolokium every month, and now we invite you to come here. Now, before you deliver your talk, I will read your CV first. Yeah. Wait a moment. Yeah, Professor Shakir Ali is now Associate Professor in Department of Mathematics, Faculty of Science, Aligarh Muslim University, India. And you have a very long CV, so maybe it is impossible to read all of them. I just mentioned some parts here that you have many research publications. Yeah, so Professor Dr. Ali Shakir also get some awards and fellowships, for example, as visiting professor, as researchers, and so on, and also research grants on some topics. I think you travel around the world, yeah. You visit many places around the world. It's very amazing to know that. And now you have many students also, and many collaborators from around the world also. And now Professor Dr. Ali Shakir will deliver a talk about commuting additive maps in associative rings. Now time is yours, Professor Ali, please.
Okay, so let me just share my screen first. So it is visible?
Yes, yes.
Yes, okay. So thank you very much, Professor Inda Vizanti, for your kind invitation to deliver a talk in your Algebra Kolokium. I'm really glad because this is the first opportunity for me to interact the people of Indonesia, especially the Algebra people. So I'm really grateful to all of you, especially the local organizing committee and the other member of your department, and especially Professor Inda Vizanti, who really keep in touch about these activities. I am really happy to see you. The topic of my talk today is commuting additive maps in associative rings. In fact, this area in the ring theory, which fill up the gap, this is work like a bridge between analysis and algebra. So in one word, if you make connection, so if we define algebra, that means defined a norm on algebra, it called functional analysis. So it is very close to the functional analysis, and mainly the topic we are discussing today is very close to the analysis. So let me give you some idea and about, of course. So I just take this opportunity to express my sincere thanks, because this work is supported by Department of Science and Technology, Government of India. And that's why I would like to express my sincere thanks to the Government of India for supporting my research. And also the members of the LOC, and especially in last but not least, Professor Inda Vizanti. Really, I'm grateful to you. So we will, yes, So we will move around according my this outline. This not it is of course big. So how much time did you allot it for my talk? Could you let me know, please?
More or less 1 hour.
Okay, good, good. Because this is a similar type of the discussion. So first we give some motivation and then discuss some notations, and the third part, the key terms of my talk, that is derivation, and then we make connection of another type of map, commuting, centralizing mappings. We generalize the notion of derivation and generalize the notion of commuting and centralizing mapping, and discuss some applications the last one, Professor E.C. Posner. In fact, this talk is based on his work and the means extension of his work. And second one is the Bracer, who is the one of the leading algebraist analyst in the area of algebra and analysis. He really did tremendous work in theory of derivations in rings and algebras. So throughout my talk, ring algebra we shall mean associative ring or algebra over a field F, and R denotes an associative ring, and ZR denotes the center of R. So with the help of R, we introduced two new product we call Lie product, denoted by this Lie bracket. X by y is equal to x by minus by x, and the another one is Jordan product, that is x by plus yx. So these notions in fact make things easy for me in calculations, so that's why they are important. Now these are very important identities which we are used time to time and reduce the calculations, and they are well known identities. Last one is very common, is called Jacobi identity, and very helpful in associative algebras. And we define these terms we use in our discussion, this additive subgroup of associative rings. So first one is Lie ideal. Lie ideal means U means the additive subgroup U of R is called Lie ideal if U belongs to U and R in R, then this Lie product also element of U. Okay, and similarly we have the means that this product in U means this U is closed under the Lie product with the element of R and U as well. And similarly, we define Jordan ideal, replacing this Lie product by Jordan product. So as I told you, because these two Lie and Jordan product are very helpful during the calculations. And the next definition is the power of Lie ideals. We call it M power closed Lie ideal. What does mean? That means if U in U, then U to the power M is also in U, where M is greater than 1 and U in U. So if this happens, then we call M power closed Lie ideal. Most of the people are working for M is equal to 2. So we call it closed. In literature, people call it closed Lie ideal closed. That means it U square in U. So we use these notions throughout our discussions. So let me give you some examples to make things clear. So any two-sided ideal is Lie ideal. That means every Lie ideal is a Lie ideal. However, the converse need not be true in general. Give example means later on. The center of ring is also a Lie ideal, and big reason is because if you commute the Lie product with R and it is 0 and it is subset of ZR, contained in ZR. So this is what. And the special type of Lie ideal construct with the help of ring with the by its commutator. So this commutator is a Lie ideal. Similarly, and this the higher commutator means this is also a Lie ideal, and also for any additive subgroup of R, RR is of course means any additive subgroup R containing RRU. So this gives the new idea. And as I told you, every ideal is an Lie ideal and Jordan ideal. However, the converse need not be true in general. So the following example justify this fact, and we consider a ring of matrices 2 by 2 matrices over GF2. That means Galba field of order 2. So Galba field of order 2. Then it can be easily seen that this U of this type, see, the diagonal, the principal diagonal has the same entries. However, the other diagonal has different. So such Lie ideal is called, such type of ideal is called a Lie ideal. Of course, this is not ideal. And when you have matrix of this type, well, both diagonals have the same entries, and then this becomes a Jordan ideal. So these are Lie and Jordan ideal, which are not ideals. Now, so let S be a non-empty subset of S. A commuting mapping F from R to R is said to be centralizing on S if Fx X means this is the Lie product in center, then the IF is called centralizing. If this Lie product is supposed to be 0, we call it commuting. However, as the topic title of my talk, the additive commuting mapping. So once this F is additive, then we call additive commuting mapping and additive centralizing mapping. So the familiar example of these mappings are identity map, of course, always satisfy because, and second one, any map having its range in the center of R, then this map must be commuting. And a map of this form, this is Fx is equal to lambda x. So this is very famous map. This is called multiplier type of multiplier. And it is very important in the functional analysis. So this is where this now the position of lambda play important role. So if this lambda is in the center, then this map is always commuting. So any question till now? Hello? Hello? Hello?
Yeah.
Oh, so I'm asking, is there any question, please? Feel free.
Oh, okay. Is there any question? So you
Okay,
can continue. Yeah.
so we will move. Now we define the one of the most important term in our discussion, that is derivations on ring. So as you know, the idea of derivation in rings came into motivated with by the notion of differential operator, as you know, are considered on the real lines. Okay, so the derivation, in fact, the generalization of the idea of differential operators, that operator will satisfy the Leibniz rule. So because the operator, they always are real line. So now we consider any ring, because ring of real numbers is also a ring. So this is the particular ring. If you replace by any ring, it may be arbitrary, it will be the arbitrary ring, maybe finite, infinite, what type of ring. So this operator we call derivation. So of course, this is additive. We all know the differential operator is additive, which is well known. So an additive mapping D from R to R is called derivation if dxy is equal to dxy plus x dy. So of course, this is the Leibniz property. So, and if you look over, if you take here x is equal to y in this definition, then it becomes x square. This, so this such map we call Jordan derivation. So look at examples. So as I told you, because they are the very common famous example of the derivation on the usual derivative of algebras, consider differential functions. This is the famous and the most important example of derivation. However, because we are talking about in the ring context, to give example non-commutative rings. So this is the, if you have example in non-commutative setting, in fact, the ring 2 by 2 matrices over Z, and the map of this type, if you operate D over here, then this is D of this is this the principal diagonal 0, and this is minus B, so B replaced by minus B, and this is same. And this is derivation on non-commutative rings. Of course, one very famous and example that always exists. So for a fixed element A of R, define a map D from R to R by dx is equal to xa. So this A is fixed. This A is fixed for all A, A is fixed and X is arbitrary. And this is one of the leap order. So by using the commutator identities, it is easy to verify such map is derivation. See here, the little bit verification. dxy is equal to x by A, and apply the commutator identity. So this can be written as x by A and then x a y. So this is what dy defined. So this is dy and this is dx. So this is x dy and dx by. So this is of course derivation. So this is always exists. You have commutative and non-commutative ring. However, in non-commutative ring it becomes 0. But okay, so such derivation we call inner derivation, and this is generally denoted by IA. A means a fixed element, and this is very important derivation in the analysis. Characterize many analysis identities with the help of the inner derivations. So now the idea of derivation in rings is not new, it is old. However, it got attention only after the work of E.C. Posner. That was the first paper on the derivations on derivations in prime ring was published in Proceedings of American Math Society in the year 1957. So this was the first paper who linked derivation and rings, and he classified prime rings and proved two very important results commonly known as Posner's theorem in the literature nowadays. The specific statement of Posner's theorem, to which we shall refer frequently, are the following. The first one is based on just on the composition of map, and second one is related to commuting and centralizing map. Now, the today's talk based on theorem B, that is commute map which is centralizing. So I will give details of this result and give several several extension this classical theorem. Let R be a prime ring. Prime rings already know, if you have two ideals, I1, I2, then the non-zero ideals, then the product is non-zero. Such ring is called prime rings. So let R be a prime ring which admits a non-zero derivation D such that x dx zr for all x belongs to R means D is centralizing. D is centralizing, and then we call such derivation centralizing derivation. Okay. So if this happens, then R must be commutative. So this classical theorem gives the new idea that is called commuting mapping. And the idea of commuting mapping, in fact, give the new theory that is called theory of functional identities. And theory of functional identities is given by none other than the Mathematician Bracer and his team. In fact, his theory solved 50-year-old Einstein problem related to the structure of related to Lie structure. So this is a very, very powerful theory, and nowadays applicable in most of the area, not in algebra, but many area of function analysis, Lie theory, Lie algebra, Jordan algebra, and so on and so forth. So the key point is the theory of derivations gives the new theory that is called functional identities. For those who are interested in the functional identities, please see the following survey, Mathematician Bracer, Commuting Maps, a survey. This is a very, very important theory, and you find more detail in this paper. So then the pupil have looked this generalization of this classical result due to Posner. So first result for in the year 1976 was Many, who obtained the same result for centralizing automorphism. That means he replaced the derivation by automorphism. And there are so many others. In the year 1973, Ram Avatar generalized the Posner's result for the Lie and Jordan ideals. So this is the result in case of prime ring of characteristic different from 2. D is non-zero derivation. U are Lie ideal, which is and D is centralizing on U. Then U is U in center of R. If U is equal to R, then R becomes commutative ring. R is commutative integral domain. So, and then another result in the same direction, but I dropped because the long list, but I give this some another important result. Yes. In the year 1987, Howard Weil and Martindale studied the comparable problem. The problem is the result of Posner for semi-prime rings and extended this classical result for semi-prime rings as follows. Let R be a semi-prime ring, U non-zero left ideal, if U admits a derivation D which is non-zero on U and centralizing on U, then R contains non-zero central ideal. Non-zero central ideal. So this is the first generalization of Posner's result for semi-prime rings. Another classical generalization of the same result is due to Lansky, who generalized the Ramotar results and Ramotar result for arbitrarily ideal. So let R be a prime ring and U a non-commutatively ideal of R. D is non-zero derivation, then D centralizing on U for all U, then either R is commutative or characteristic for different from 2, R satisfy S4. S4 means the standard identity of degree 4. Standard identity of degree 4. And then we will extend it in more general setting, and that is called Angel condition. For all x, means till now, if you notice, we are working for the commutator, just for commutator. Okay, this is a commutator of order 1, and henceforth we are moving on commutator of higher order, order 2, order 3, order 4. So here we define the commutator of order n, that is called Angel condition. For all x by in R, define x by means this is the first commutator, first order commutator, same as x by minus by x. And then we define the nth order commutator x by k, the kth order commutator, that is equal to double, see x by k minus 1. This is for this another, and this is y, where k is greater than 2, then the fixed integer n greater than 1. And the angle condition is a polynomial x, Lie vector x by n is non-commutative variable. In short, you can say this is nth order commutator for the associative rings. So the example is very simple because any commutative ring satisfy a commutator. Okay, or any commutative ring satisfy this nth commutator or in n variable. So this is the, and now then the first result in this direction are the classical result for second order and third order commutator was due to Joseph Bookman, and who proved his result, the result for second and third order commutator, which is as follows. Let R be a non-commutative prime ring of characteristic different from 2 and 3. Suppose there exists a derivation D R to R such that the mapping, so if you look over here, right in the way of commutator, so this is dx d by, and then because this is centralizing, so that means the double, this is second order commutator, they're talking about the second order commutator. In that case, if D satisfy this condition or D is centralizing on non-commutative prime rings, then D becomes 0. And further, Bookman and Ashraf extended the above mentioned result for the third order commutator in the setting of semi-prime rings. In fact, in view of Posner's theorem, they mainly showed D is commuting. However, if you look at the more general result, and that is by Bracer, let R be a prime ring of characteristic different from 2, and suppose there exists an additive mapping. So from derivation to just additive mapping. Okay. If any additive mapping satisfy the second order commutator, then this IF must be commute. Okay. So this is the another generalization of result due to the Bookman. The most famous and classical generalization of Posner's theorem is due to Lansky in the year 1993 for nth commutator. So let R be a prime ring, I a non-zero ideal of R, if D from R to R a non-zero derivation of R, such that dxx, that is k, D satisfy the kth order commutator, then R is commutative. So for k is equal to 2, you have Posner theorem. For k is equal to 3, we have Bracer's theorem and so on, Bookman theorem and so on and so forth. This is the another generalization of all these results. So let R be a semi-prime ring and D is non-zero derivation of R. I is non-zero left ideal, and if for some positive integers k0, k1, k2, kn, and x belongs to I, guarantee this holds. Then di is 0, or else di and dri are contained in the non-zero central ideal. In particular, when R is prime, then R is commutative. This is the now. Another direction that introduced or initiated by commuter centralizing map, that is in the year 1993, Matthew Bracer characterized the prime rings or commuting mappings in prime rings. Means he mainly described the structure of additive mapping on prime rings. So the result is the following. Let R be a prime ring. If an additive mapping F from R to R is commuting on R, then there exists a lambda and C. C is the extended centroid of R. And additive mapping Xi from R to C. Then every commuting and centralizing map has this representation. Every commuting and centralizing map has this representation. And fx is equal to lambda x plus xi x for all x belongs to R. So this is the one of the application of centralizing and commuting mapping, and that is called functional identities in general. Now we come on the extension of derivation. So we call it generalized derivation. Generalized derivation means the map, in fact, if you look on this ax, x by, so if you look on carefully, this is the left multiplier and this is the right multiplier, and we take some of these left and right multipliers. So this gives some new type of map, and we call such map inner or derivation. In fact, generalized inner derivation, because already we discussed the inner derivation, and here if you take this is negative, that is inner derivation, and if A is equal to B, if you take B is equal to minus A, it becomes inner derivation. So in fact, this generalized inner derivation is generalization of inner derivation as well as derivation. Anyway, so let me see how this happens and how it generalize these all things. So inner derivation we have already mentioned like that. Already we have discussed this. This is here generalized inner. So look, the additive map F X, this is AX, XB. A and B are the fixed element. And if you take I, this is inner derivation determined by the fixed element A, that is AXXA. Now combine these two, then the fx by, calculate x by, replace the x by. So this is what fx by is equal to fx y and x, y. So this is what, this is in a derivation. So we write IB, and this is only additive map. So one is additive map, another is part is the derivation. So combine this, and this gives the idea of generalized inner derivation. So motivated by this idea, in the year 1989, Mathematician Bracer introduced the following notion. An additive mapping F from R to R is called generalized derivation if there exists a derivation D of R such that fxy is equal to fxy x dy holds for all xy belongs to R. So here I emphasize the terminology. Look at, this is additive map, F is additive map, okay. Now then there exists a derivation. So this F is just additive map combined with the derivation, okay. So this is called generalized derivation. And of course, because F is additive, if you take F is equal to D, so it includes the notion of derivation. And hence, the idea of generalized derivation is the extension of derivation. Hello?
Okay.
Hello, yeah.
Oh, I'm sorry.
You disappear. No, but we can continue now.
Okay, so we are talking about how the notion of derivations involved in the function analysis. So this making the connection between analysis and algebra. So when D is 0, the fx by is equal to fx by. This is in fact called left multiplier. So left multiplier is very important. Our theory of multipliers is very important in the function analysis. This is also remarked that the theory of derivation plays not only important role not only in the rings, but also in the function analysis. An extensive and deep theory has been developed, especially for derivation of C-star algebras, operator algebras, and commutative one-off algebras. So anybody interested in this area can be look these references. These are totally based on analysis, like centralizing, mapping operator algebra, continuous derivation of one-off algebra, lift centralizer, and isomorphic. So these are the idea of means derivations, idea of derivations involved in the function analysis. Now, in the year 2004, Albas and Aligarh extended the Posner theorem for generalized derivations. So the result is the following. Let R be a prime ring if R admits a generalized derivation f from R to R such that fx x belongs to, that means f is centralizing, then R is commutative. So as I told you, f is, if you take f is equal to D, you will get the Posner's theorem. So this is the first generalization of Posner's result for generalized derivation. And then in next, the Aligarh and Carini and De Philippis generalized the above result for Lie ideal and for nth commutators. So let R be a prime ring with extended centroid C. F is generalized derivation of R, and U a non-zero central ideal. U is non-zero central ideal of R, and K is positive integer, means fixed integer, and this kth commutator holds for all U in U, then either F has this form. So F has this form, Fx is equal to Ax. That means F is a left multiplier. So a map which satisfies this condition is none other than the left multipliers. And here this A comes from C, or R satisfy the standard identity of degree 4. So here the C, we always using the term the extended centroid, in fact. So let me just give you briefly. Means if R is prime, then the extended centroid becomes a field. So, and if it is a field, you know, this becomes commutative ring. So the meaning of A, that means A is in commutative ring. So A can commute to each other. This is the meaning. Further, they proved the same result for more general setting, but I skip, and now we move. In the year 2012, me and my co-worker, Professor Dhara, generalized the several results of Posner, Bracer, and Bookman and Ashraf for generalized derivations. So the result published in Journal of Algebra and Applications, let R be a two-torsion free semi-prime ring, and FD, this is just a notation to make things simpler. IF associated with D. Okay, we a generalized derivation on R, and if this is, you know, the second order commutator. So this is second order commutator. Okay, that means F is centralizing. Then D maps R into its center. D maps R into its center. That means D is commuting. In fact, in general, you can see. In particular, when R is non-commutative prime ring, then there exists element Q in extended centroid C, and in that case, F has this form. That means F is left multiplier. So, and this result, in fact, gives the tools, means algebraic tools. We use these algebraic tools in the functional analysis, and we characterize some notions in the CSR algebra. So we will discuss later on. Further, the idea of centralizing and commuting mapping were extended into n-centralizing and n-commuting mapping in the year 1995, and the idea of the n-centralizing and n-commuting mapping was given by Ding and Well. They defined as, let S be a non-empty subset of R and n be a positive integer. The mapping F from R to R is said to be n-centralizing, respectively n-commuting, if fx comma x to the power n. So for n is equal to 1, we call centralizing and commuting. So this is the generalization of centralizing and commuting mappings. And then they prove the following result. Let n be a fixed positive integer and R be n torsion free. N torsion free means nx is equal to, means n is a least positive integer, nx is equal to 0 implies x is equal to 0. So R is semi-prime, n torsion free, I is non-zero left ideal. If R admits non-zero derivation D, such that these non-zero and is n centralizing. That means dx and x to the power n in center, Lie vector, the center, then R contains a non-zero central ideal. We extended this result in more general setting. Look at this. This is for derivation and R and torsion free. And we extended this result for generalized derivation of additive subgroup. So let n be a fixed positive integer, R be an torsion free semi-prime ring, and I is an additive subgroup of R, which satisfy such that x to the power n plus 1 in I. That means, if you remember the definition of n power closed ideal, so this means I is closed with this n plus 1 power of x for all x in I, and f d generalized derivation of R, which is, if f is centralizing, f is n centralizing, then f is n commuting. That means every n centralizing map is n commuting. Okay. However, the converse, every f n commuting mapping is always n centralizing. The question is, does converse hold? So this theorem also gives the idea about the converse of converse part, that is n centralizing is commute and commuting, and n commuting is n centralizing. So this is, and of course, if you take I is equal to R, so you get the result just mentioned in the last slide. So, and this result, in fact, has very nice corollaries and very means gives this some new type of idea. So let n be a fixed integer, and next R be n plus 1 torsion free semi-prime ring, f d a generalized derivation of R. If f is n centralizing, then f is n commuting. That means every n centralizing mapping is n commuting on semi-prime ring. And the next result based on the Lie ideal. So let R be a 2 torsion free semi-prime ring, and L be a non-zero square closed Lie ideal. Square closed Lie ideal, as I mentioned in the before, if you take m is equal to 2, then that means u square, if u is a Lie ideal and u is element in u, and if u square also in u, then we call square closed Lie ideal. So if fu means f is centralizing on square closed Lie ideal u, then f is commuting. In particular, when R is prime, then I'll contain in the center of R and contain the center of R. The next theorem generalized the result proved by Bookman, as I told you, because the nth commuting and nth centralizing mapping gives the many new ideas. So, however, the approach of the proof is not same as the previous authors. We use the different approach in the proof. Means we use the theory of the functional identities, in fact. So that's why this result is very, very important. So the result is the following. Let R be a 2 and 3 torsion free semi-prime ring, I and additive subgroup. So we see just on additive subgroup. So that means it may be Lie ideal, or Jordan ideal, whatever you can say. Means those, it's really some problem for ideals or Jordan ideals or ideals. Okay, we include all these results in this particular theorem. So I, an additive subgroup of R such that x squared in I for all x in I and f d a generalized derivation of R. Now, if the map x fxx is centralizing on I, so the notation is that means the second direct commutator is 0. Then this f is central commuting, and once f is commuting, then by using the previous result, we characterize or we describe the structure of this additive map. So we have more results in the same paper for nth commuting mappings. So let n be a fixed positive integer and R be n torsion free semi-prime ring with extended centroid C, I a non-zero ideal of R, if generalized derivation, and if fx means if is n commuting, then di is 0 or di is contained in non-zero central ideal. This is what the classical generalization of Posner's theorem means, Bracer's theorem, published in 1993. In particular, when R is non-commutative, then this centralizing, commuting generalized derivation is of the form fx is equal to qx for all x in R. So that means every n commuting generalized derivation is a left multiplier on non-commutative primaries. So this is this, and as the application, we characterize these maps in the next few slides. So, and the one-sided version of the above mentioned result is the following: let n be a fixed integer and R n torsion free semi-prime ring, I a non-zero left ideal of R, f d generalized derivation of R such that this D is non-zero on the center of R and f is n centralizing. Then I d z are contained in Z or R contains non-zero central ideal. So in the next 2 or 3 slides, we will discuss the application of our results in function analysis, how the algebraic tools are helpful to establish the results in the functional analysis. So the first important application to characterize n centralizing and n commuting map on C-star algebras. C-star algebras are well known in functional analysis, and why C-star algebra is because it's very, very important in functional analysis. It has good connection, C-star algebra, some algebras like C-star algebra, one Newman algebra, operator algebra. In fact, they have close connection with the prime and semi-prime rings. So that's why they are make a bridge between ring theorist and analyst. So the first classical application of our result for centralizing mappings is the following theorem. Let n be a fixed integer and A be a C-star algebra, FD a linear generalized derivation of R. If F is n centralizing, then F is n commuting. That means every n centralizing mapping is n commuting on C-star algebra, So that means on the C-star algebra, these two notions are same. On C-star algebra, these two notions are coincide. the next result, we describe the structure of the generalized derivation. So let n be a fixed positive integer and let A be a C-star algebra if the linear generalized derivation. Then if this f and d is n-centralizing on A, then either A is commutative, that means C-star algebra becomes a commutative, or f has this form. fx is equal to qx plus dx for all x in A, q in C, and this dA contained in the center of it. So that means every linear generalized derivation, centralizing linear generalized derivation on C-star algebra has this representation, Okay. So in short, you can say we describe the structure of n-centralizing generalized derivations on C-star algebras, and this is the particular form of this result. And so these results, in fact, just we make on the conclusion, we start from the Postner's theorem, that is commuting and centralizing derivations. And then one way is to study, means to find the structure of ring, and the another way is to describe the structure of additive maps. So this is what we make conclusion. So we find the structure of, by using the theory of derivations, we describe the structure of rings, prime or semi-prime rings, or we describe the structure of additive maps if we fix the rings. So that's enough, and thank you, everyone.
Thank you, Professor.
You are welcome. If you have any question, please.
Yeah, it's very interesting. Is there any or some questions from audience, please? Okay, maybe I will ask a question for you, Professor Ali.
Sure.
Yeah, I saw in some results, theorem or corollary, that the assumption of primeness of the rings is needed. This is
yes.
Why the primeness is important here.
Sometimes because we not put here the counterexamples, but if we remove the primeness, the result may not be true. Means we have counterexamples. Yes. Okay. Means like, for example, you have commuting derivation. Okay. So if you have prime ring and D is non-zero, then R is commutative. This is the Postner's theorem. Okay. So if R is not prime, then there exists derivation which satisfies this condition, but R may not be commutative. So that's why the primeness is the essential requirement.
Okay. Thank you. Another question? Okay, I think it's no question from the participants. And once again, thank you very much for Professor Shakir Ali for nice presentation. It's very interesting. You connect the algebra and analysis here, functional analysis especially. It's very nice, yeah. And I will deliver the message from our head of department. He cannot join us today, but he sent his greetings for you and also for the participants, and he suggests that these activities between Indonesia and India, between Gajah Mada and Aligarh University, continue in the future. So it is very, inshallah, yeah, it's very nice. And okay, maybe this is also a message for all participants. Please fill the the form in the chat. In the chat, you can
Okay, there are, I think there are 3. Yes, read, please read.
Yeah.
This is from dear all, please fill the following. I think
Yeah.
okay.
Yeah, this is for participants. But
Okay.
don't worry, for you, we have special for you. You not necessary to fill the form. But for all participants, please
make announcement. Make announcement. Those who are joined this participate means this seminar, Kolokium, can get a certificate. So please fill up this form. And if you need a certificate, the team of Aljabar Kolokium, they provide you the e-certificate.
Yeah. Thank you. Yeah.
That's good. That's fine.
You can, choose English or Indonesian. Yeah.
Yeah. Sure.
Okay. And for you, we have the certificate also. We will show you, and for the participant, I will share screen here.
So I will first I think I start my screen.
Okay.
Yeah, sure.
Okay. So you can see this certificate.
Yeah, mashallah. Thank you.
Yeah. So this is our appreciation for you. For your
thank you very much. Thank you very much for your whole team. I think there are many people, head of the department, chair of algebra and laboratory. Mashallah. I'm happy and thank you very much for your love and affection for such wonderful gift. I remember it.
Yeah, you're welcome. And please keep in touch with us for this activity in the future. Maybe next seminar, or maybe we can meet in conference. Who knows? Yeah.
Sure.
I hope you can.
Yeah. Just little one announcement for the Turkey conference. Please announce in your group for the Turkey conference. We have a special session for algebra.
Oh, okay. Yes,
and because you are the member of scientific committee, so you can check and make publish in your group. They can send paper or presentation also. If somebody are interested to give talk, let me know.
Okay. Yeah. So I will announce. Yes. Thank you very much. I will announce it to the Indonesian. Yeah.
I hope I will be in Turkey, inshallah. So if you join, that's very fine.
Okay, thank you. Jadi ada konferensi internasional yang di Turki ya. Silakan yang berminat ya itu. Yeah.
If you anyone need the proper invitation for the means, then let me know. Okay, for algebra session, because I am dealing the algebra session.
Okay.
I make the invitation. Otherwise, for paper presentation, they send the paper to the conference and they CC to me. So I make record in my group.
Okay, ya. So beliau akan membantu kita ya. Kalau kita berminat, silahkan kita beritahukan ke beliau, gitu ya. Oke, terima kasih. Thank you very much for all. We can close this Kolokium.
Okay, thank you.
Thank you very much, and see you in the next event. Inshallah.
Maybe do you have some activities like, because as I know you are president for the Indonesian Math Society. So do you have any conference of annual conference from the Indonesian Math Society?
Yes, we have Indonesian conference and also international conference. International conference, international mathematics.
When it will be held?
For Indonesian conference in October. But the international conference in next year.
Next year, okay. Next year.
Still,
very good.
Still have time to prepare.
Yeah, sure.
Paper or something, yeah.
And
also maybe we will ask speakers from if we need speakers from international.
Yes,
I will
be message and.
I will ask your suggestion. Yeah, not only algebra, maybe another.
Alhamdulillah, we have very big group, like not in India but across the globe.
Okay.
We have good algebra people like the Lopez Sergio Bisbal, Tariq Rizvi, and in Turkey, in India. So that's very welcome. Just let me know. We will keep in touch all these people.
Yeah. Okay. Thank you very much. Okay, then we can say goodbye now for all participants.
Thank you very much. Thank you very much once more, and also thanks to Isnaini.
Oh ya, harus naik. Ya. Terima kasih Mas
So
Wahab.
Isnaini, thank you for very this.
Yeah.
I am happy really, and to be happy to see you all, because this is my first interaction with the Indonesian mathematicians, especially the algebraists from Indonesia.
Thank you very much.
So that's why I'm really happy to see you all of you. And you are most welcome anytime. Please feel free to just write me or whatever. You have my mobile number also on my email.
Yeah, I have.
And so either you send message, I am keep in touch.
Yeah. Okay.
I'm really happy to be the part of any activities if you need.
Yeah. Okay.
And any collaborations or any I don't know, because we have some collaboration from Indonesia, some university in Islamic studies before 2 years. Islamic study, Department of Islamic or Faculty of Islamic Studies. So you maybe it will go in the Faculty of Science as well. If somebody or something you need, just let me know.
Yeah. Okay. Yeah. Thank you very much. Thank you very much.
Yes, we can manage.
It's very nice.
Okay. Thank you very much, and assalamualaikum.
Goodbye. Assalamualaikum.
Yeah. Okay.
Terima kasih semuanya. Silakan.
Thank you.
Thank you very much. Yeah.
So let me close the room.
Yeah. Silakan.
See you in the next event.
See you. Bye bye.
Bye bye.